Good afternoon, and welcome to today's Richard M. Karp Distinguished Lecture. So my name is Umesh Vazirani, and I'm the director of the Quantum Computing Cluster at the Simons Institute. So I think many of you are quite familiar with the Simons Institute, and you know what a wonderful place this is. But there are a few people who don't, so let me just say it's a wonderful place. Okay, it's sort of a unique institute of its kind. It's the only one that is devoted to theoretical computer science. But it's unique beyond that because it's also an extraordinarily interdisciplinary institute, which is organized around this theme, this view of the computational lens into the sciences. I should say that the Richard M. Karp Distinguished Lectures, they celebrate the role of Richard Karp, who anybody in the field knows of as one of the founders of theoretical computer science. He was also a founder of the Simons Institute, and he was the founding director. And of course, we are grateful to many contributors of the Richard Karp Fund who actually fund the institute and make this series possible. Okay, so now let me introduce our speaker, James Whitfield. It's really a pleasure to have him speak here. So James, well, we know him well at the institute, but he is currently an associate professor of physics at Dartmouth College. He got his PhD at Harvard with Alan Espero-Guzik. And his dissertation was one of the first, maybe even the first one, to really take quantum chemistry algorithms and really express them as quantum circuits. He is currently working at the Amazon Web Services quantum computing effort with a special emphasis on training and education focus. James has visited the Simons Institute a number of times, and he's been one of the people who's really introduced us to quantum chemistry and fermions, and today he's going to talk about the complexity of fermions and quantum information and beyond. So please join me back.
Thank you very much. Okay, so thank you very much for that wonderful introduction. I'm very happy to be here to be giving this talk, and I wanted to really say thank you for this invitation. I've been coming to Berkeley since I was an undergraduate, and the first time I came as a guest of the chemistry department, and that was when I first got exposed to computational chemistry. And it's nice to come back almost full circle to think about just computation and quantum information science very broadly. Today's talk, we're going to focus in on fermions and think about how these things can help us understand different data structures that are of interest. Okay, so just to kind of start off the talk with a little light joke, why can't you believe fermions? It's a classic, because they make everything up. Well, not everything, but they make many things up. So in particular, neutrons, protons, and electrons are examples of fermions. And these are the type of particles that we're going to think about. But we're going to think about them as fermions rather than as physical particles, because we're going to think a bit about how we can understand the computational properties thereof. And so as an outline for the talk, I wanted to give an introduction. I wasn't sure exactly what everyone's comfort level with quantum mechanics was, so I wanted to start off with a bit of quantum mechanics from the concept of probability first. That'll help us motivate the idea of indistinguishable particles. And then from there, we'll talk about the simulation of fermions. We'll talk a bit about quantum chemistry and quantum computers, but that won't be the focus of the talk. Instead, we'll focus on antisymmetry and the algebras for qubits. That'll lead us to a new data structure that we'll talk about at the end, and that'll be the highlight of the talk. Okay. So first, let's start off with just a basic discussion of how probability works inside of quantum spaces. So if we think of probability vectors, just a vector of numbers. These numbers need to be normalized. They add up to 1. All the numbers need to be greater than 0 and real. We can just organize them inside of a vector. When we go and think about this vector, we can then reorganize this vector as just a matrix. in that matrix, we just make sure it satisfies the same properties as the probability vector. We can generalize this further and deal with the off-diagonal elements, and these are the quantum coherences. And so when people speak of quantum decoherence, it's the loss of these off-diagonal elements that restore the ordinary interpretation of probability theory. And this is the probability density matrix. I think it helps conceptually when you think of it as a probability density matrix rather than just a quantum density matrix. And this is our central object. And so what I'd like you to kind of glean from this is that even if you just know probability, this is a good way to get a handle on quantum mechanics. This probability density matrix has eigenvalues that also satisfy the same conditions as a probability density vector. And so this gives a very nice analogy between quantum and probability theory. So I guess the crux of this small introduction is just that quantum theory is an extension of probability theory. This takes care of all the notions of measurement and all the complications of interpretation and shoves them back into interpretations of probability theory. So I'd also like to emphasize here that this talk will mostly be focused on the states. Many of the things that I talk about could be reformulated thinking about the operators instead. However, this focus on states will help us uncover how we can think about fermions and their intersections with other types of particles. So brief introduction to quantum mechanics out of the way. We now turn to multi-particle states. Here we can think about what happens when we have a set of states that are each individually describable, separable states. So we have a probability vectors, just Cartesian products of 1, 2, 3 of each state. We have the same idea for our probability density matrix. Again, just tensor products instead of Cartesian products. And this is how we build up our states. Then we want to think about how permutations act on these states. So this is going to get us to start thinking about indistinguishability, start thinking about how antisymmetry comes into play. So this is an example of our permutations here. What we have is so we have our permutations here. The permutations in the middle are all of the transpositions or swaps. These will play an important role inside of most of the discussion today. We'll be thinking mainly about how the structure of the swaps plays out. The other permutations are products of one or more swaps, and always an odd number of swaps. An even number of swaps, excuse me. Okay, we'll turn to that in a moment. So if we think about the particle permutations, how this permutation from some permutation groups is swapping these objects acts on these states, which should swap these tensor spaces, or these Cartesian spaces in the case of probability vectors. So we swap our probability space 1 and 2 with an example at the bottom. And then we can think about the same idea of swapping these matrices. What's important to note is that because we're thinking about a 2-index object for the matrices, we now have these operators acting on left and right when we write down the representations of this permutation. Again, an example of just permuting 1 and 2. So we just permute the two spaces. And this is just the idea of permuting spaces and thinking about what these swap operations are. So now moving on to what it means to be indistinguishable. And this is where we get into this notion of fermions and also the notion of bosons. We think about indistinguishability. We think about things that are identical and can be swapped around. So if we have, for example, these screws here, if you swap one screw for another, nothing changes. So when we talk about indistinguishability, we can talk about it with respect to nothing happening when we do a permutation of those two objects. So with that notion of indistinguishability, we can write down our indistinguishability conditions here, that we need this permutation to do nothing to our state. So when I swap the probability that the first object is a screw or a nail with the probability for the second object, this can be very important if you need nails or if you need screws. And so this swapping of operations is not, would make them distinguishable. So we think about indistinguishability for ordinary probability states. We just have only one way we can do this, where this permutation operation just gives back a +1, and it acts trivially, and this is called the trivial representation of the permutation group. Okay, so now when we think about the indistinguishability conditions for the quantum state, we can think of this as something acting on both the left and right, but we still want it to be invariant under any particle swaps. So we don't want anything to change when we change the states, the particles within our state. This gives rise to two different representations. We have the alternating representation, and we have the trivial representation. The alternating representation being either +1 or -1. With it being -1, we still have -1 acting on the left and -1 on the right. So -1 squared gives us back +1. So the state remains invariant regardless of whether you use the alternating or the trivial representation. Okay. So I think here's where we split our notion of what type of particles we're talking about along what type of representations we're looking at. So we have fermions, we have this alternating representation, and we have bosons, we have this trivial representation. This would be particles like light, or in the case of fermions, it would be particles like electrons, or quanta of electricity.
Sorry, question?
Please.
There's something that I lost in this process. Yes. So can you say the sentence about bosons? Bosons are going to be something that's invariant under some of these permutations?
Yes, so it would be invariant under all permutations, so it'll carry the trivial representation. I can give a couple of examples in a second, but you want to think of a carrier of the trivial representation as something that when you do a permutation, you get back a plus sign, and nothing changes, so it stays completely identical. For the fermionic case, because we're going to act on the left and right, when you swap it, you're going to get a minus sign, but it'll be on the left and a minus sign on the right, and then the product of those will give you back the same state.
So, I see. I'm used to thinking of things acting simultaneously on the left and right by their adjoint. So,
Yes.
Could I?
Well, the adjoint of -1 is still -1.
Yeah. So, but I don't see that if I do both at the same time. If I do the left and the right action, I don't see the difference.
Yeah.
Okay. But then you're saying, okay, but underneath there are some states that if you did only one, you'd see the difference.
Yes. In fact, I think the right way to think about that is what are the representations of the permutation group. And so the one-dimensional representations of the permutation group are the trivial and the alternating representations. All the other representations are going to be larger dimensions, so then you need two copies of your state in order to carry it. Does that make sense?
If you take a pure state, then that swaps the recipe.
Okay. Is it good? Okay. I have some more examples, so hopefully it'll clarify as well. So when we think of symmetric or anti-symmetric, when something's symmetric under some operation, here we have just the parabola x goes to -x. This is symmetric under this because the function f equals x squared remains f equals x squared after performing this operation. On the right side, we have x cubed, and if we take x goes to -x, then we have -x to the third power, which gives us -x cubed. And the function picks up a minus sign, otherwise stays the same. When we think of this, I think getting to the question that we just had about what do these states actually look like, we can think of how we actually create states that carry the trivial or the anti-symmetric representations. So in the case for the trivial representation, we just take every single permutation, add them up, and then when we act that on any state, it will be invariant to acting with another permutation after that. So this is just called symmetrization. And so on the left-hand side, you can see this is all the symmetrizations of ABC. So we swapped around ABC, BCA, CAB, and so on and so forth. Then on the right-hand side, we have the alternating representation, and this is a completely anti-symmetric space. This means that it picks up a minus sign whenever we act with any permutation. So whether we act with permutation AB, permutation CA, we can see that we will get a minus sign. And so this is anti-symmetric for all swaps. And this is the way you should think about how we split up these two types of operators, these two type of representations for the permutation group. Okay. Right, and as maybe a kind of highlight summary of this introductory section is just mention of the Pauli exclusion principle. So why do we discuss all this? There are physical consequences to this. So if we think about what we carry as a representation, if you carry the antisymmetric representation, you can't have two particles in the same place. If you have two particles in the same place, then that state is necessarily zero. Here's an example where A equals to B. And so this is just a general case of the Pauli exclusion principles that you can't have two things in the same place just due to this anti-symmetrization requirement. Okay. So here's a good place to pause and see if there's any questions or any thoughts at this point.
So there's something I'm confused about this representation part. At the beginning, you defined P sigma to be swapping positions, right?
So sigma is just a general permutation.
Sure, but you define, I don't know, you define sigma on the state, and it was permuting, and now you're defining as a representation of that operation?
Yeah, so yes, exactly. That's the representation of that operation, exactly.
Okay.
So we think about how we actually write that down. It's here. So on the first line, you have the group element acting on the set of states. And on the second, you have the representation acting on the states. And so we're looking for the one-dimensional representations. And that's the alternating or the symmetric. And that gives us the bosons and the fermions.
So what's the space of rho n here in the second line? It's a one-dimensional thing.
No. Rho n is this is a tensor product of many 2 to the n dimensional matrices. So here.
Okay.
So we have rho n, the dimensionality at the bottom. So d is your local dimension, and you have d raised to the n by d raised to the n, and that's the size of the matrix.
Okay. Okay.
All right. Good. Okay, so that's my somewhat technical introduction to fermions, but hopefully also pedantic. And so what we're going to do now is think a little bit about how this goes into applications to kind of zoom out a little bit before we go into any more technical discussions of fermions for the moment. So what we're going to first think about is quantum chemistry and quantum computers. So as I mentioned, the first time I came to Berkeley was to visit and to think about quantum chemistry. So let us go there, but go there stepwise. So when we think about this antisymmetric and symmetric subspaces of our states, please.
So I was just trying to understand, so to try to get Pauli exclusion principle from this antisymmetric thing is that if the two particles are at the same place and you swap them, then it should be the same state, but it should also be negative, and therefore it should.
Yes, that's correct.
Huh?
That's right.
Okay.
That's right. So the exclusion principle is just is a consequence of the antisymmetry. Okay, so as I said, this talks mostly we've talked about states so far. We could also think about operators. These operators can also be invariant under permutations. So we think of a Hamiltonian that acts over many particles but acts identically between these particles. Then again, the permutation operation will do nothing to that state. And then we can block diagonalize it by these states. And so bringing that into some of the consequences in physics of quantum computing, I thought I would go through 3 quotes or 3 main ideas over history. Going back to Dirac, and this is 1929. It says here, the underlying laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws lead to equations much too complicated to be soluble. This is a fantastic concept. So he's saying that these equations are very hard to solve. However, we can use these equations to build quantum computers, and then those quantum computers can help us understand those equations, and so you get this fortuitous cycle around this Schrödinger equation, or this Hamiltonian here. And so understanding this gives us some insight into what's going on. I will note here inside this quote that it's very interesting. He says a large part of physics and the whole of chemistry. And I will turn to that a little bit later towards the end of the talk. Actually, in a couple minutes. So one other thing I'd like to point out is the next quote I'd like to bring up is this quote from Richard Feynman. I don't want to say it because it's a little not PC. However, nature is not classical, so you need to use a quantum computer. And this is really one of the things that we're going to think about is how do we use quantum computers to think about fermions. When we think about putting fermions on the quantum computers, well, the qubits are individual qubits. You have qubit 1, 2, 3. And you can think about how to address each qubit. They have different addressabilities. You need different ways of controlling the qubits. However, fermions, being all indistinguishable, you can only control them collectively. And it's very hard to think about one, or not hard to think about one fermion. It's hard to interact with a single fermion when it's in a cloud of fermions together. Okay. So the third person I'd like to point to inside this brief journey of ideas is John Popel. So he won the Nobel Prize in 1998 for developing this notion of model chemistries. And this hopefully will connect to some of the main ideas about how we should think about what is complexity for a quantum chemist. And so when we think about what quantum chemistry asks for, he gives this very wonderful Nobel Prize lecture on quantum chemical models. And he talks about how you start off with the model, and you have some target accuracy for that model, say thermal energy at room temperature. You have some formulation of that model, say theoretically you pick mean field or you write down a matrix product state. And then you have some implementation. For quantum computing, you could use Amazon Braket, or you could think of using density functional theory or C++ or different languages to implement. And what I really want to focus on today is validation and prediction. I think there's a lot of work that's gone on into formulating and implementing quantum algorithms. And just to say a few ideas here about what we're actually trying to do inside of quantum chemistry is just say that there's a lot of reactions that occur. And they occur at room temperature, or maybe they don't occur at room temperature, and you want to know what is the case. You want to know what is the reaction rate. You want to know different properties. And all these things are mostly dictated by energetics of the system. And so what's at top is a energy function. And this energy function here is some function of the nuclear coordinates. So where is this proton? Where is this chlorine atom? Where are they at in space? And then there's the nuclear charges, some set of charges, and some number of electrons. And then as you change the number of electrons, or you change the nuclear charges, and you move around the nuclear coordinates, you can ask what are the energies. And so that would be this conformation where you have all these hydrogens in the plane, and you have 2 hydrogens out of plane, 2 hydrogens in the plane, and that's just a different configuration of these R values. And so the whole goal of quantum chemistry is to parameterize this, this function. There's many ways of doing this, and one of the ways that people check that they've made improvement is by just looking at many, many test cases like the 3 that I just showed, or 4 that I just showed. So all these different chemical reactions that, different chemical reactions that you can do, these all occur, and you have some experimental evidence or high quality theory evidence, and then you want to test out any new method against what's already been done. And so that's the validation step. And so one of the things that I think we should be focusing on as a quantum community, I think both as technologists and theory of computing, and both ways to think about how do we actually get data from doing quantum computing for quantum chemistry in order to predict when quantum primacy will actually occur. So if we had test results from 2020, from 2021, 2022, and 2023 of some test set of molecules, even if they're all terrible, it would still give us confidence to say how things are going in the future. We'll also say that if we choose quantum chemistry as a route towards quantum primacy and we find that we don't actually need a quantum computer for it, that's actually still a fantastic result because it says that we've also formally solved quantum chemistry, which should also be of use for quantum chemists. Okay, so a few ideas. Now, pause for questions here. If not, we're going to go a little deeper into the algebra and the mechanics of fermions. So what we're going to think about now is occupation number vectors. When we think about occupation number vectors, these are vectors that say whether or not a mode is occupied. A mode could be an orbital, could be a location. You can imagine the chairs inside the room, and each chair being occupied or unoccupied. I pick a canonical ordering for which chair is first, second, third, and then I say whether the chair is occupied or not. This is going to be enough for me to keep track of the system. I also want to be able to keep track of the phases, and so I have to be a little clever about how I keep track of the antisymmetry that I want to encode for these to remain fermions. So to keep track of the antisymmetry, we need 3 things. These 3 things are a vacuum state, we need lowering operators and raising operators. And these are operators that allow us to change these numbers from 0 to 1 or from 1 to 0. And our lowering operators are 2 to the n by 2 to the d by 2 to the d operators, which you can already see because there's 2 to the d possibilities, because each occupancy can be either 0 or 1. So they act inside this entire space, but they need to act according to some algebra. And we're going to talk about that in a moment. However, the first thing we want to point out is that the vacuum state itself needs to be inside the kernel of all of the lowering operators. So this is how we're actually going to define the vacuum state. And so with that definition of the vacuum state, we can think about how these operators need to behave in order to make sense as an antisymmetric space. So to give some notion here, again at the top we have these occupation number vectors, and just as a reminder, the occupation number vector is ordered, so A0, A2, A1, A2, A3 in order, and that order doesn't change. We write down the occupation number vector, even if the operators change orders. Okay? So when we think about the rules for antisymmetry, the first rule is that if we have two operators, AI, AJ, and we swap the order of them, we need to pick up a minus sign, because that is a permutation, it's a swap. Okay. The second case, we have a lowering operator and a raising operator, and we swap them. Again, we need to pick up a minus sign because we've done some transposition swap operation. And then on the third point here in the right, if they happen to be the same value, I and j are the same, then we not only need to put in a minus sign, but we're also going to annihilate them. We're going to just take them both out and replace them with the identity. So this is the idea that we're going to have raise lower, and you raise lower, you just don't do anything. And so we need to do that with the correct phase. And so the minus signs here are very important for preserving all the algebras. Okay. Hopefully it's a motivation for the canonical. Yes, please. Don't have me go too fast.
But you had the analogy of the room with people sitting down, and that was sort of to indicate the locations were sort of ordered.
Yes.
Right?
Yes.
What are these A operators are acting on an individual chair? How should I think of the A operator?
Yes. Let's go through an example. Yeah. All right. All right. So how should we think of the A operators? These A operators are raising and lowering operators. So if I do an A with a dagger on it, I'm going to raise the occupancy from 0 to 1. If it's 0, if it's 1, then I'm just going to throw everything away and set it to 0. Here's an example of thinking about how we do this antisymmetry. So how we do this antisymmetry is that we have some state here with the occupancies labeled. So the occupancy 0, 1, so it's 1, 0, 1, 0, 1. And this corresponds to the state of having each one of these A daggers showing up. And that's what you see here. So A dagger 0 shows up because this is occupied. A2 shows up because this is occupied. A4 shows up because it's occupied. And so these show up, and they all act on the vacuum to take the vacuum, which is all 0 state, and put those particles into the vacuum state where they belong. Okay. Now if we want to add in a new particle, we add in A3. Well, this A3 is out of order, and we have to put it back in order. We're going to put it in order using the algebra that we have. And so the first step is that we're going to take A3, A0, and we expand out our operators, and we're going to swap A3 with A0, and we're going to get a minus sign for performing that swap operation, 0, 3. Then we're going to get another minus sign swapping 2 and 3. Oh. Get another minus sign from swap 2, 3, and that's swapping 2, 3 here. And then we end up with minus 2 squared, minus 1 squared, and then 1, 1, and then this 1 filled in where 3 goes. Okay, the last state's wrong, but the concept should be there. So can I correct this? So what I would like you to note here, one thing that I would like you all to note is that what we did is counted the prefix. So we counted this 1 and this 1, and we put a minus 2 here, and then we changed this from a 0 to a 1. Okay, a little messy here, but there's a second example. Well, one example. Yes, please.
So you're saying AJ and AI are not commuting. but
Yes.
they're acting on different positions. So how to understand that, like why they're not commuting?
So they don't commute because we want to keep track of the minus signs. We want to keep track of where the minus signs are.
So you just set them to be not commuting.
Yeah, so the whole construction here is to make sure that whenever we swap anything, we get a minus sign. So we built these operators just to make sure that they always put in the minus signs correctly. Whenever we reorder anything, we're going to get back the minus signs correctly. So that's the way that we're keeping track of the permutations. So anytime you swap it, we just put the minus sign in there. And then if we have to remove them, that's the only time this rule comes in. Everything else is just from swapping them. I think it gives a better motivation than thinking of them as anti-commuting. This just says that when they do swap labels, you have to put a minus sign there. And that's the way that you should think of it. It's an implicit representation of the permutation. Okay. So any questions on that example? Sorry for the typo. But, please.
So if they're creation operators and they're acting on, so should we just think of them as acting on the corresponding Hilbert space? So there's a tensor Hilbert space here.
Huh?
There is?
Sorry, is there a tensor Hilbert space?
There's a different particle, whatever, n0, n1.
Yes.
ND, this is the tensor Hilbert space, right?
This is the density.
I mean, we're just, we think of n0, n1, etc. as
Occupancies. Bits.
occupancies, but for
Yes, some space. Yeah.
but that space is a tensor space, right?
Yes. It's a single particle space, and it needs to be an antisymmetric space. So tensor product wouldn't necessarily be antisymmetric.
It's not tensor?
Tensor products aren't antisymmetric. You know, you have A tensor B.
And so I guess problem, so AI is not local. So you might think of n0, n1 as qubit, but the lowering and raising operator will be chain of polys. It's not local.
We'll do that. We'll do that separately.
Although it's just raising a particle at that location, but still non-local.
So whether or not it's non-local is something you can make arguments about. The non-locality of it, the way that I would think about the non-locality of it is because you force this thing that's not necessarily linear to be in a line. You've picked an ordering that's 1, 2, 3, 4. Now, to go back to that ordering, you're always going to have to take anything in 3 space and put it back into a line. And so that's part of what you're doing by just having these things labeled 1 through D. You picked some labeling for it anyway, so you've already forced something that's going to need the minus signs later.
But if you want to think of qubits, it is not going to, right?
Well,
If
yes.
you want qubits in your mind, then the operators are going to.
Non-local?
If you would like to have qubits in your mind instead.
We'll do qubits. We'll get to qubits. And it will be non-local when we get to qubits. I can give some constructions for what these operators look like in terms of Pauli matrices. But for now, we should think of them as 2 to the D by 2 to the D operators that are just acting on the space according to this rules such that everything remains antisymmetric. And so it's just a way of making sure you always have manifestly antisymmetric states. Question?
I guess, is it, I know, I think you referred to that you're going to get to this later, but for people who are used to thinking of like the model of computer scientists thinking of things, then this raising operator that acts on the ith space sort of puts in its plus or minus sign conditioned on what it's seen before that. Is that how I should think about it?
Great. You've queued up the next slide. Here we go. So what you're pointing out is exactly right. You're looking at the prefix sum. So you're looking at the sum of all the bits to one side of it. And that prefix sum is what you need to compute to figure out what that phase is. So you have -1 raised to the prefix sum. So you need to compute the prefix sum every time. And so that's where everyone's saying it's non-local. Right? So computing the prefix sum, you can't do that locally if you just store the bits. Okay? And so this shows up in problems like the cumulative frequency tables. I didn't get a chance to type this up, but however, if you have a cumulative frequency table and you want to change this number from a 97 to a 98, well, I also need to update all the ones that included that number. And so this sort of prefix sum update rule sort of You know, whether you have a bit or prefix sum, or you want to update the prefix sums and the bits, this sort of game shows up in other places. However, for us, we're going to think of it in terms of fermions. And so what's important here is this definition for the prefix sum. This is the sum of all the bits less than the prefix that you're asking about. These bits are 0 and 1. Again, for us, in this talk, we're going to think of these bits as being the fermionic occupancies. However, don't limit yourself, okay? This notion of non-locality shows up in the most simple way of thinking about the qubit representation. So thinking of the qubit representation, you can write down the Jordan-Wigner transform. I'll walk through an example in a second, but the Jordan-Wigner transform is this idea that you put inside of each one of the qubits just the occupancy of that mode. So you can do that game. I think someone mentioned it already inside the audience. And so the idea of putting each qubit as representing whether the mode is occupied or not gives rise to this notion of the Jordan-Wigner transform. This is 1928. And so again, I said I'm not going to focus on the operations as much as the states. But what you should think is that this Jordan-Wigner transform is computing the prefix sum. So you see here this is k less than j. So just even intuitively, you can see this is computing the prefix sum. And then you're doing some raising lowering operator with this x plus minus y. So holding on to this sort of intuitive level, and we'll go into some more granular thinking in a moment. However, at this kind of high level, what you're seeing is that these z operators that show up here are computing the phase. They're getting the occupancy to know whether you should have -1 raised to the n or -1 raised to the k. Whatever number it should be raised to is just whatever your prefix sum is. And then you're also raising and lowering appropriately, and this is just what the exponential looks like. So when you think of what this causes on quantum computers, depending on how hard it is for you to compute your prefix sum, is how non-local your operator becomes when you think of it as qubit operators. So you can't compute the prefix sum, or you can compute the prefix sum, but if your prefix sum takes order d, then your overall cost for doing the simulation is going to be order d, just to compute what the prefix sums are. All right, so let's walk through an example for Jordan-Wigner. I've written out the states a little clearly, hopefully. And so what we can think is just multiplying out these matrices following this Jordan-Wigner rule. So A4, here we're counting from 1. So 1, 2, 3, 4. And you have z's at everything less than 4. And then for A2, you have a z at A1, and you have the s minus, taking from 1 to 0. And so we multiply this out, and we have z times 0 here. Z times 0 gives us a +1, and this is fine. So we get back no minus sign. However, if we do the other direction, we go through the same mathematics. Z times 1 gives us this -1. And so you can see that this is A4, A2 is equal to minus A2, A4. This is Jordan-Wigner. When you think of the non-locality of fermions in terms of qubits, normally people refer to the Jordan-Wigner to think of this being highly non-local when thinking about what happens. We can think about why it's non-local, and it's non-local because you have to compute this prefix sum. So even thinking of this just as a data structure, right? If you want to compute the value, you just look at the qubit. If you want to update the value, you just look at the qubit and flip it. And if you want to do the prefix sum, then you just look at all the qubits less than that. But that's order d. Right, so this is your first sort of linear cost inside the problem. Okay, now you could be clever and say, well, maybe I don't store inside of every single qubit. I'm not going to store just the bare occupancy. Maybe I'll store some sum of occupancies. If I store some sum of occupancies, I can get out a number of different encodings. So one encoding is just called the parity encoding, where I just store inside of each qubit the parity. So inside of 0, it's just 0. Inside of 1, it's 1 plus 0. Here, this is x1 plus n2, and x1 is n1 plus n0. So this is all the bits up to x2, x3, x4, x5, x6. So this is just saying that we can store the parity. However, if we store the parity, then looking up the prefix sums is just order 1, because we just looked. Looking up the value is also order 1. However, updating the value is now order d. Right? So if I change this bit to a 1 or for 0, then I need to update every single bit to let it know that the numbers, all the parities have changed. And so you can think this is not winning the game because you're still paying a linear cost.
So the overview of what you're describing is different ways to sort of try to
Yes, that is exactly right. That's what we're doing. It ends up being the same problem in a cumulative frequency table as it is inside of fermions. And so when people talk about the operator picture for this same thing, you can think of this in terms of Pauli X, Y's, and Z's, in terms of Majoranas, and I'll mention that a little bit, but this is really think of it in terms of data and how we're storing this data and what does the structure of that data look like. And so it actually gives a very nice connection to kind of go beyond fermions and think about what are we looking at. Okay. Along the same lines, there was in 2002, Bravi Kitev wrote their very famous fermionic quantum computation paper. And in it, there were many ideas that were very esoterically written and a little tough to pull out. In 2012, 10 years later, there was a paper by Jake Seeley and Peter Love and a co-author where they just elucidated the mapping, just kind of walked through kind of what was the idea, kind of expounded upon it, kind of looked at what the optimality conditions were, did some analysis, and it's a very pedantic paper. And so what they found inside there is that you store a mix of occupancies and partial sums at each qubit. And so this is just the map. And so if you look at the top, there's a diagram. And the diagram here, each arrow is indicating which is being stored inside of that bit. So if you look at 7, 7 has an arrow to 6, an arrow to 5, and an arrow to 3. And you have N7, 6, 5, and 3. And so these are all being added to put whatever you're going to put inside of qubit 7.
Is this like a binary tree?
Hey, fantastic. That is absolutely right. That's the very next thing. The Fenwick tree, the binary tree, exactly. Yeah, in 2017, we're sitting around with some computer scientists, and they told us, hey, that's a binary tree, just like this, right? Yeah, that's pretty much it, right? Just like, hey, and it's like, great, someone thought of this. And so this also allowed us to generalize it beyond what they had done inside the quantum fermionic context, so you can start thinking about how does this work for things that aren't necessarily powers of 2. Okay, so great. Around computer scientists, they've heard of binary index trees, this data structure from Peter Fenwick. Okay. Please.
So this suggests that somehow, I don't know, I saw previous pictures with 1 and D, and now I see 3 log D. That suggests better or not?
Oh yes, better. So it's better because you've now traded the costs of doing the prefix sum and the cost of doing the lookup and update off. So it's now you're paying the same price for everything.
And so is this, let's see, is there something you can say about, so if we were trying to, so did this make certain computations that people cared about doable that weren't doable before?
Yeah. I mean, this table, or this construction, the data structure itself, widely used. The top coder, I mean, you can find tutorials. You can find better tutorials. All the stuff that I'm saying about how this index table works is on top coder. Tutorial walking you through it. Here's how to code it up. Here's how to get order D time, 10 lines of code. So it's very cleanly thought through. Okay.
And then the difference that makes was that different enough that sometimes you can improve things, but the computations you really want to do have an extra factor or something.
Sure. So the computation sure has many other factors in it, right? We didn't get any detail about how to actually exponentiate these things, but the locality properties of this are strictly bad. Right, so you can see the locality is at worst log D, other one's linear. So this is really what we're thinking about here. Just think about the locality and how many entries I have to access. So just as a game for the moment. Okay, so just to be clear, if we think about occupancy N4, so if we have N4 here inside this particular table, if we want to update N4, if we want to update N4, we change N4, but we need to change everything that has N4 in it. So N4 is here, but it's inside of 5 and it's inside of 7. So all the green ones we need to touch and update. If we want to get the prefix sum, we only need to touch 1 qubit. Just so happens that 4 is next to a parity store for the lower half of the tree. And then if you want to read it, you just look immediately where you're at. Okay. All right, is this reasonably clear, everybody? Please.
I guess this is relevant for solving problems on a quantum computer. But is this representation also relevant for solving chemistry problems on classical computers?
Oh, chemistry. I don't know if it applies to chemistry. I mean, it's useful for a lot of things inside of cumulative frequency tables. I don't know. I don't know. I'm not explicitly. Does that answer your question?
No, my question was more like, is it relevant only for quantum computers or also for classical computers?
It's relevant for classical computing. I wouldn't say for classical chemistry, but for classical computing. This is data structure. And so this data structure has many applications just to updating tables and looking up entries in it quickly. And so just as a data structure, this has applications. And so what I wanted to say now is I want to say that, you know, in going through all these things, we've thinking about data structures, thinking about quantum operators, well, we've been able to come up with a new data structure that has applications the same way the Fenwick tree has applications, just by thinking about quantum computing.
Just thinking about time, we are now entered the question here.
Okay,
just
just
so many questions, we can continue. And
almost done. So I'll just point out a few things, and then we'll leave all the details for the questions. Okay. So there was a paper in 2020 that I really liked from the Google group, and there's been several papers from Algorithmic also building upon this work, Zoltan Zimborsch and others. And what they did was come up with a way of getting a log3 locality for the qubit encodings. So this is really interesting because you went from log2 to log3, so it's an improvement. They do it by looking at the operators. And what we've done is gone back and gotten that log3 using the data structure. So the cool thing is that this is data structure. You can just use it for whatever you want. And the idea is that we just built it up from thinking about Sierpinski triangles, just connecting these nodes out. We connect these nodes out. And this is analogous to how the Bravik-Gatev encoding can be thought of in terms of Fenwick trees, thinking of this in terms of how these arrows are connected to one another. So we can now build up a different type of tree that then has log base 3 cost for doing all the different updates. So the central node connects to node 7, connects to node 1, and then these nodes have their neighbors also connected to 2 nearest neighbors, and so on and so forth, that the tree just grows from there. Okay, I will go to my final slide and just say that, yeah, it's log base 3 for the update for the central node. Order log base 3 for evaluating the values, and order log base 3 for using the data structure. So the idea is that we now have a new way of thinking about how to do cumulative frequency tables, which hopefully has applications to everywhere people are using the Fenwick tree. So that's the main idea, the punchline, and hopefully you guys learned a bit about fermions, thought about how probability and quantum mechanics intersect, thought a bit about quantum simulation. This work was done with my research group. This is a picture of them kind of hacked together. In particular, Brent Harrison was a lead on this project, really thinking a lot about fermions inside of our group. Andrew Prjansky and Jason Nikes also were on the project with me. And then Casey and Weisher are thinking a lot about how do we do benchmarking on quantum computers. So that's what our group's doing outside of what I've talked about. So.
we still have time for more questions.
It seems you are just solving a prefix sum problem using data structure, and it's like the dynamic prefix sum problem. So is it true that any data structure that supports dynamic prefix sum will be translated in this scenario?
Yeah, so I mean, for fermionic operators, you need to compute the prefix sums as well as occupancy. And so anything that would just allow you to do that more efficiently, do that with touching less bits. So the locality of the operations is what's dictating the complexity for the quantum computation, or at least how non-local the gates will be when you do the evolution.
So the locality means like probe complexity in data structure? Like how many cells you need to probe?
Yeah. So the way that you can think about that for the case of thinking about how this translates over to states is that if you want to do the fermionic state, you just need to compute the prefix sum, and that prefix sum is then going to allow you to do the operation. So
I guess my question is, like all these things seem seems classical because you just prefix sum. So it's like every classical algorithm to do the prefix sum can be like used here.
Yeah. So so certain classical structures for sure, with the idea being that the locality of the operation that you have to do is dictating how large this is going to be as a quantum operation. So here, what is the locality of this operation is going to be dictated by how you're computing that phase. So if we compute the phase by actually touching every qubit between P and Q, then that's going to be linear in P and Q. Now, if you have a better way of storing the data, what's between P and Q, then you have a better way of doing that. If you can do that more locally, then that translates to savings inside of your quantum algorithms.
Okay, thank you.
Hey, thanks for a nice talk. So actually coming back to this previous question about these like fermion to qubit mappings, whether they're also relevant for classical computing methods for quantum chemistry. I don't really know exactly how it works, but when people use MPS methods, like when they do DMRG for quantum chemistry, I think they're also doing a Jordan-Wigner transformation kind of, and would it help there, or do people also use these different qubit encoding methods, and would that be good for MPS algorithms or not?
That's a great question. I think it's very interesting. I think if you do an MPS algorithm by directly transforming the spins, then this would be relevant. I think there's other tricks to doing MPS simulations that might avoid the entire conversation. So I don't know.
All right, thanks.
More than
Any other questions?
Is this the best encoding possible?
No. So even the data structure that we have, you can optimize it just by actually pruning edges. And so you can we have a brute force method of optimizing it. So right now it's just the right order. I mean, it's just a better order. And the nice thing is that we can prove that it is the optimal order just because of the actual results from the quantum result. So we can actually use the quantum result to think about how optimal our data structure is. The data structure is not completely optimized. It's the only reason that it's not optimal. But we actually rely on the proof from the quantum case, so it's a nice direction. Go please.
So far, the optimal encoding is about a single creation or annihilation operator, right? So when you consider a linear combination of fermionic operators acting on multiple orbitals, and the optimal one can be quite different. Is that right? So could you comment on some of the state of art on efficient encoding of this multi-linear combination of things?
I don't know that I can comment much on the state of the art of it. I think it's a fantastic idea, and ideas occur to us. I think perhaps even equally interesting as thinking about multi-particles, you could also think about things that are in some other symmetries besides just anti-symmetry. So if you thought of projecting into, say, a particular spin state, that might also be possible, and that's more of a multi-particle operation that you also think about how to project into some particular eigenstate of other operators. I think it's interesting to think about how you would encode geminals, but I don't know. I don't know anything about it. But it's a great idea.
Is there a distillation of what the idea is that makes you able to move from binary to ternary trees? Is there somehow, is it like, what's the, if I press you on what the core thing or feature is?
So I would say from my perspective, I think the core thing is actually, at least from the quantum perspective, is that when you think about Jordan-Wigner, you're really relying on the Z component of the spin system to store all the information. When you go to the Bravik-Kitev transform, you're using Z and Y, and starting to mix in other operators. And so when you think about what they're doing here, they're actually using X, Y, and Z equally. And so if you think of actually balancing across X, Y, and Z, then you can imagine that log 3 shows up naturally. Now, why that shows up for the data structure, I don't know. But it makes sense to show up from the quantum point of view because you have X, Y, and Z for these operations that kind of give you this log 3 intuition.
Else? If there's no one else, then we'll stop exactly on time. So, thanks, James.
Thank you.